Any questions?
All right, so I have a parallel plate capacitor separated by a distance of 10 centimeters. Each plate in the capacitor is 5 meters by 5 meters, but this is huge. But the distance between them is tiny compared to, or small compared to the size of the plate. And so we can assume infinite plate approximations. Okay, so
what is the subgroup on the first D and the last?
this is the electric field strength of the plates. This is total and dielectric. I think there are a lot of problems on the test where I don't have the dielectric one down, but I have the others. All right, so first off, are there any easy answers?
We can find out the plate's electric field pretty easily.
Okay.
Just doing Q over A. I forget what that symbol is.
But we got an A. Do we know Q?
That's the. Would it be the change in voltage?
Try again. Volts.
Change in volts.
I guess that works. It's either voltage or change in potential. I was nitpicking. But. All right, so what is this across the capacitor?
Like all around it?
Just from here to here. 20 volts. Yeah, it is 20 volts. Technically, the way, if we're nitpicking, which, sure, why not? I've already done it to Jack once. I gain 20 volts going, so if I do my loop like this, I gain 20 volts here, I have some change in potential here, and when I get back to where I started, I should be at 0. So if I added 20 here going to the left, as I go across the capacitor to the right, what is the change in potential?
Negative 20 volts.
Yeah. So technically negative 20 if I'm going this direction, it's negative 20 volts. It's positive 20 volts if I'm going this way. And so 20 volts is what I'm looking for here, though. I probably should put that around it. Which of the two plates of the parallel capacitor is positively charged?
Well, because we just talked about if we were going this way, you're losing volts or
Losing potential.
yeah. Would it be the one on the right? Because when you're going back this way, that's gonna be positive. You're gaining volts.
Think about it, alright, so if you're saying, speculating that's positive and that's negative,
Yeah.
so if I go from negative to positive, do I gain or lose?
Gain.
Yeah, so since I'm losing going this way, that's gotta be the positive, that's gotta be the negative. Also, the positive plate is attached more directly to the positive lead of the battery, and the negative is attached to the negative lead. Alright. Other people than Jack can play the game, although, you know, Jack and I can carry on the conversation. Alright, so I got the positive plate here, my negative plate there, and we can, there's no red on this thing. I don't know why. Makes me wonder if one of these is supposed to be red. Positive plate, negative plate. Positive. Try that again. Positive plate, negative plate. Of course. Come on. There we go. All right, so now so we know what the voltage is.
What are the words for each?
That,
Yeah.
plates, so this is the electric field strength for the plates alone. This is the total. And this says dielectric.
I forget, is the kappa for the big C coulombs different, or is that constant, like the 8.99?
Oh, no, it's not that one. Kappa in this, that actually is a K, 8.99. The kappa is the dielectric constant for
Whatever.
for free space. If there's absolutely nothing there in between, kappa is 1. If, for the lab that you did yesterday, I expect kappa to be somewhere between 1 and 3. Well, ideally.
Well, then we can solve that one.
Yeah, okay. So, the capacitance therefore, plug and chug, since epsilon sub naught is a constant, area, I gave you information, D, I gave you information. So it's 1 times, I don't know why I'm writing a 6. 8.85 times 10 to the negative 12 times my area of 25 divided by 0.1. What do we get? Somebody's gonna tell me an answer.
You have it right.
That's right. Except for,
The units.
which are,
Coulombs? No. Yes.
Yeah.
no. C is for capacitance, this C is for capacitance, not for coulombs.
Newtons per coulomb. Coulombs per meter squared.
Well, we can do it the old fashioned way.
Oh, Farad.
There we go.
Farads.
Or 2.2125 nanofarads. All right, so we have the capacitance. And now just recognize that this is about on order of the kind of capacitance we were getting yesterday. But we're dealing with much smaller plates, but we're also dealing with a much smaller gap between them. All right, so I now know capacitance, I know the voltage. What else can I find?
Q.
How?
You multiply capacitance with voltage. Then
Okay. So we're using, oh, I didn't write that over here. So we also have capacitance is equal to Q over delta V. And by the way, this is always true. This is true for a parallel plate capacitor. But this is always going to be true. So if you have a spherical capacitor or a cylindrical capacitor, which they generally don't do with 152 because it involves calculus. But this is always going to be true. All right. So what is the charge then?
No, that's right.
Oh, that's right,
Yeah.
except for,
That -8.
that's an 8.
Yeah.
What are the units? Yes. And let me just say, I don't want the tears of sadness to roll down my face when I realize some of you don't know that coulombs are a unit of charge on the test. By the time you get around to the test, I hope you know coulombs are a unit of charge. Looks like you're about to ask a question, Tristan.
Nah, I'm gonna the plates.
Ah, okay, yep.
Would it be the -20 volts over
Say it again.
the -20 volts over the 0.1?
20 volts over 0.1, which is
200
all right.
volts.
And now that pesky thing at the end.
Volts over here.
Oh, okay. Or that's fine if you left it like that. But what's another unit?
It's newtons per volts. Or if I have it backwards.
No, not backwards. It's newtons per.
No.
There we go. Now, technically, what Tristan just found, in this case, yes, that is the electric field from the plates because I have nothing in between. However, the voltage divided by the distance between them, that is really for electric total. So this is the total. So, as just revealed.
So for the dielectric, because it's just air, we use that kappa constant.
No, you would use the kappa constant for the,
Oh, it's the
what are the places?
so 0. Yeah.
0. Now, if there's error in between, error does have a dielectric constant, but it's like 1.0003 or something like that. Close enough. This is a government institution, therefore it's government work.
Can you explain how we got the plates?
Tristan told me.
What, can you explain how we did that?
Tristan, can you explain how you got this?
The voltage over the distance between the two places or time.
Using this formula right here. Okay. Which sometimes will be written as delta V is equal to, if you're ignoring direction. And again, this formula works if the electric field is constant in space, as opposed to time. All right, other questions before I change what's happening here? Then let's change what's happening here. All right, so now I'm gonna disconnect the battery. Discombat. What changes?
Well, we know the Q is constant, so the Q is the same.
Okay. I'm gonna do something. I'm gonna put a little Q sub 0 there, just so we can do everything in terms of Q sub 0. And we'll call this delta V sub 0 and C sub 0, E sub 0. Okay.
I think we talked about this yesterday. If you remove the battery, the voltage stays the same. Or is it?
If the battery's disconnected, Q is the same. Because the charge doesn't know where to go. Now, let's add a touch of reality here. If I hooked a capacitor up to a battery and then I disconnected it, when I disconnect it, I have to be able to disconnect it fast enough so that there's no spark. If there's a spark, I've suddenly lost charge. So whenever I'm disconnecting the battery in problems like this, it's an ideal, really fast disconnection so that I don't lose any in the actual disconnection. In reality, you do have to disconnect it quickly in order to maintain the charge.
Why?
Because?
Like what about it going slowly is gonna cause a spark?
The fact that the electrons have this buildup of pressure and they want to move. Well, actually, let me think about this for just a moment, because I have electrons piling onto here. Did I overgeneralize it? Let's see. So I have electrons piling onto here, pushing the electrons off of this. So it's going to reach some steady state. Then, different situation. Thank you for challenge. In this particular case, no, it's not going to do it. There is another case. Do you want me to go into the other case now, or wait? Go for it. Still not quite sure which one you said.
Go for it.
Go for it. All right. If I've got a battery here with a capacitor and a resistor. And so as I do this, the current's going to be flowing this way. It's going to be flowing both routes. At first, there's not going to be much resistance caused by the capacitor when it's not fully charged, but then over time, this will become harder and more current's going to flow that way. So if the charge the capacitor fully, then now I have a current flowing around like this. Because the capacitor can only take so much charge. If I then disconnect it, so that I just have a charged capacitor and a resistor circuit, or also known as an RC circuit, then, let's see, I have a bunch of electrons here, which are trying to get over to here. And so when I do that, the current's gonna shut off, but I have these electrons which have built up, which, oh wait, the electron's going the other way. I've done this so many times, and yet, let's see, so I have positive charge there, let's move this, I have to edit the video. And current flowing this way, so I still have current flowing like this. If I disconnect, electrons flowing like that. Oh. If I disconnect it slowly, I still have electrons which are moving off of the negative side of the battery, and they will spark to there. With those excess electrons, well, they're not gonna go that path. They're gonna go this way, and then they will match up here.
Is it like the electrons are still trying to finish the circuit as you're pulling it out?
Yeah. And so the more electrons that jump, the more neutralized this plate will be, which means more of these electrons will go off and you lose charge of the capacitor.
Okay.
In the world.
And the world ends. It's possible. It's possible every moment, also, every moment in time